Okay. Hi, everyone, and welcome to our session, Anti-Cheating Tool for Massive Multiplayer Games using Amazon Aurora and Amazon ML Services. That's a mouthful, I know. My name is Yoav Elat. I'm a product manager at AWS. And with me is Yav Biran, who is a solution architect who has worked for a long time on the gaming industry. And together, we're going to show you some techniques that you can use to detect cheating in games based on data that you have in your relational database. So let's look at the agenda for today. So first of all, we'll talk a little bit about machine learning and relational databases in general. So not just the gaming example, but just in general, what kind of data do you use for machine learning and what happens if it's located in a relational database? How do you run ML models on that type of data? We'll talk more specifically about our example, which is cheating in video games. So think of people who are writing a program that will play on their behalf, or two players that are coordinating with each other, some kind of cheating behavior. And at a very high scale, you need to have some kind of automated way to detect those kinds of situations and deal with them. We'll look at the cloud services that we're using. Obviously, we work for AWS, so we're using AWS examples, but I think the same type of ideas you could probably use using other databases or other clouds if they have similar capabilities. We'll do a walkthrough of our solution using a game that was developed here at Amazon, and we'll show some algorithms that can detect specific types of cheating, and we're going to look at 3 types today. And then some next steps for how you can add machine learning to your application, whether it's a game or whether it's other types of applications. So when we think about machine learning, obviously that's become a huge topic in the software industry in recent years, and especially, we see it a lot at Amazon, a lot of things, both at AWS in terms of the cloud and Amazon's other businesses. And usually when people think about machine learning, the more instinctive way or the more highly visible way that people think about it is for things like text, when it analyzes what you're saying or translates it to another language, or images. There's services where you can send a JPEG and it tells you if it's a dog or a cat or a horse. I have a friend who actually worked on horses and on bicycles for a long time. So, looking at examples and, training a model to identify these things. So these are things, or self-driving cars or all these other machine learning examples. But what is actually much more common is that you have very traditional, relational, tabular type of data. And there's a huge percentage of the world's information that is sitting in relational databases. And the question is, what do you do in that scenario? You have lots of data and you want to be able to take the data from your relational database, use it in a machine learning service, and get results and make predictions and put that inside of your application. So your application would be able, the one that's sitting on top of your database should be able to go select some data, run a machine learning model on it, and get some prediction. And there's many different cases where you might want to do that, and we'll look at some examples. So traditionally, it used to take a lot of work and a lot of machine learning expertise in order to add machine learning to an application. And we've counted at least 6 steps that you would traditionally have to do. And you, meaning both you as an application developer or database user, and with some help from a machine learning, data scientist or someone who is an expert in those things. So first of all, you would need to select in the plain language sense, to select a model that would work on your data. And usually through trial and error, you would find an algorithm that works on your data, and you would have to train it. You would then write an application, some code in your application that would do select in the other sense, to read the data from your database. Then you would need to format it. And formatting is often really a pain in the machine learning world, because different algorithms expect data in different formats. And even if it's a format that it's a CSV file, what order are the columns, all kinds of problems like that. So you have to do a lot of work to format the data for the machine learning model. Then you need to run the model in a machine learning service, probably in the cloud these days. Then the service needs to format the output back and then feed it back to your application in the original format so that your application can go and do something with the results. So that's a lot of work. And the result that at least we've seen is that most machine learning is really done offline. We don't see a lot of cases where people are actually making calls from from an application to a machine learning service. It usually happens, usually the data scientists will just take, like we're showing in this diagram, that will go and read some data from the database in some desktop tool and then go do some experimentation, or maybe the model is already there. They'll run the model, call the service, run the model, and then load the data into the database or forward it to the application owner. So the whole thing often happens offline, and sometimes people are running scheduled jobs, but even that's less common. What we would really like to do is to just be able to add some code to your application, to your game or whatever the application is, and then use the models directly from there. So that's what we want to show today. And these problems would be even bad enough if you only had a single data source. So if you have an application like a customer service application that has a database where all your customer service records are located, or an order management system, or IT management that looks at events happening in your data center, all of these things, and you just need to pull from one data source, that would be bad enough, and somebody would need to sit with a desktop tool and do that. But it gets even worse where you have multiple data sources. And the gaming example is definitely a situation where you have multiple databases to look at. There's different things that happen in the game, including the moves that people are making in the game, plus the data about the players and all kinds of other things like that. So if you have multiple databases, you need to go and get all that data, combine it, load it, and then run it. Then you would have to, you'd be sitting and calling multiple algorithms, and you would have to go and combine all the results and reconcile them. So that would be a lot of work to do manually. So we want to see how we can do that in an easier and automated way. Okay, so like I said, gaming is an example where you have multiple data sources. Today, we're going to look at three things. One is authentication, so the information for the players that logged into the system, and to see if there's anything fishy about what some player did when they authenticated themselves. There's transaction data, which is what players do, what they buy inside the game. These are good examples of supervised learning because it's a pretty structured type of data, and it's tagged properly. You know exactly when somebody logged in, logged out. The fields are pretty well known in advance. And then for player moves, that's a little bit more difficult to classify because they're moving in all directions, and you're not exactly sure like what is a valid move and what is not. So that's more of an unsupervised learning example, and we'll look at both of these cases. Okay, so a few things about the cheating problem. So from what we've seen from research firms like IDC, it's a really serious problem. So think of two players that are, moving together and Yav was telling me about these examples where two people are coordinating, where one of them is walking in front of the other and acting like a sort of human shield. So people shoot at the other player, that player dies, and the other player can continue to move, and then they switch roles later. So, when you do things like that, or when you write automated software to play on your behalf, where you have a player that's walking in one direction, shooting in the other direction, and doing 5 other things at the same time, then it's probably a bot that's been written. And it kind of takes the fun out of the game. And like you can see in these surveys, people are kind of losing the fun in the game. And I think, similar issues exist in other industries. So even in video conferencing, like we're doing now, when we're using Zoom to speak, there are problems where you see bad behavior from participants. And if you could automate some of the obvious cases where somebody is disrupting a conference or any other type of software that you have, then it can make it much more playable and usable. Okay, so a few words about the technology that we're using, and then we'll jump straight into how we develop these algorithms and how they work. So we're using Amazon Aurora, which is a relational database that's offered by AWS for those of you who are not familiar. It's compatible with MySQL and PostgreSQL, and both of these additions support these machine learning capabilities that we're talking about, and they were released at the end of last year at our reInvent event in 2019. And it's basically a different it's a data this is a database that's based on the MySQL and Postgres databases with a bunch of optimizations and performance improvements, plus a few additional features. And it has pay-as-you-go pricing, which is like a cloud service. You pay for what you use. The machine learning capabilities specifically, which we added in 2019, what they basically do is allow you to do a query in your Aurora database and then transfer it to a machine learning service for making a prediction. The two services that we support currently are SageMaker and Comprehend, which are two machine learning services that are offered by AWS. And the nice thing about it is that the whole thing is done using SQL queries. So you don't need to call APIs, you don't need to write additional code. You're basically doing you can just write a statement where you're selecting from the results of the machine learning call, and it's a function, and you can just use the results just like you would use any other type of data that you get back from your database. So if we look back at the 6 steps that we had before, using this feature, you basically get it down to 3 steps. So you still might want to select and configure the machine learning model using SageMaker or whatever tool you want to use. Now you would just run a query that calls the SageMaker, in this case, service, and you would get the results and you would use them in the application. A lot of the things that I mentioned earlier around formatting and all of that are done automatically behind the scenes. Okay, so before we go into the gaming example, just wanted to show a few other examples of what the select statement might look like, or what the SQL statements might look like in different examples. So the first example is when you're looking for fraudulent transactions. That's obviously a very common use case where you might want to use machine learning. So in this example, we've made some we've committed some transactions, and we have a function that we wrote which is called is transaction fraudulent, and it takes a few columns of data from your table. And if it returns true, then you want to roll back that transaction, and it was fraudulent. So that would be something that you would check when you actually insert it into whatever final table is where the transactions are officially approved. Second example is using the other service, Comprehend, to do sentiment analysis. So this is an example where we're looking at text, and you're passing a text that somebody wrote. For example, it might be somebody said about your product on your website. So, this product is excellent, this product is terrible, or whatever, and you want to look at the sentiment of what they said. And if it says positive or negative, you can go and you can take action. So for example, in a customer service example, you would maybe run sentiment analysis on the comments that people are making, or the reviews, or the customer service requests that they're making. And if somebody makes a negative statement, maybe you want to go and follow up and do something about that. And then the third example is a classification example, where you have customers that, a database full of customer orders, and you want to look at what they bought, and you want to look at other data that you have about those customers, where they live, age, gender, whatever it is, and then you can predict what kind of customer are they and what they're likely to buy in the future. So you might discover, your ML algorithm might discover that you have 5 types of customers. One of them is big spenders, the other ones are occasional spenders, or whatever. You want to classify them into different groups. And once you find the customers who are likely to spend a lot in the future, maybe you go and you market something to those guys. So different things you can do. And in all of these examples, it's very likely to be relational data that's in a relational database, whether it's numbers or whether it's text. Okay, So I think with that, let's hand it over to Yav, and let's look more specifically at what the gaming scenario looks like and what we built here.
Right. Hi, everyone. So, as you have mentioned specifically about the gaming scenario that we're gonna take a look at this presentation is that we already got we decided as a business, as the business problem, for about the dimension of the problem. So we looked at the game and we saw that the game enable you to do all kinds of stuff, such as moves, or such as buying loot or other transaction that you could do. And obviously, in order to get into the game, you will have to authenticate. So that's the three transactions, the three dimension that we are going to take a look at. Now, what we did behind the scene, like a cooking show style, is that we already built the model. We could take. I'm gonna mention it a bit on the process of that, but just for the sake of this demo, we're going to assume that we have models that are deployed in our machine learning tool called SageMaker, and those models are exposed as an API, and they send you something, right? They send you, most of the time they send you a number that will give you, that will basically be the prediction with some sort of efficacy, which will be represented in another number. So in our example, we're going to have an authentication cheat score. This is and this, as you can see in the function, how we are integrating with this with the model. It is basically a standard create function statement that defines the dimensions that the model accept. In this case, it's the user agent, and I'm talking about the authentication, the user agent, that the device that the customer came and performed the authentication, the day, the month, the hour, and the minute, and the source IP that was used. Now, all these parameters will be sent to the SageMaker endpoint that it's called auth cheat, and in return, it will give you the score. It will return the score that we wanted, right? As we could see on the right side with the select statement. Now, in order to filter that, what we did basically, we created a classification that the results of this request will be in a new column called classification, CLS, and we are basically filtering all the classification that are greater than 0. Now, this is a private case, right? Because we are using a regression, a logistic regression, which is basically a binary results. But you will see in another example, when we use anomaly detection, it's going to be something else. And we're going to talk about how do we determine what will be the classification score that is interesting for us to review. Now, this is the game. This is a game that was that we developed in reInvent 2018, where we wanted to talk about completely other things, but just to give you an idea of what is this game ought to do. This is an MMO, a massive multiplayer game, and it's basically enable you to go on this surface and execute all kinds of stuff, right? And the execution can be literally executing people, but also performing other transactions. As you can see, this is all kinds of events that are happening. Ideally, we would like if we would have this this presentation with you in a conference. We would let you play it and actually sense it and emulate the cheat, but unfortunately this is not the case. But I'm sure we're going to have another chance in the future. But to our point, we simulated some sort of a cheating activity that is done across the 3 dimension that we mentioned before, and let's see what's going on. So we're going to start with the authentication. As I said, player authenticated with a supported client, can be PC, game consoles, anything basically that that your game supports. And then you have the emulants that are defined in 5 personality traits and game events. They can move, forge, dodge, etc. And also, finally, they can transact virtual goods. So what does cheating look like in the data? Now, you have mentioned that before, that the cheating can manifest in various ways. And the beauty of this feature is that it allows you to decide on what this cheating means. And then it allows you also to respond or to react to how cheaters become reacting to your measures. So and maybe this is a good point to make, that the machine learning based solutions works very well with problems that are evolving and they're not static. And so in our case, player can cheat as they make illegal trades and run bots. And we will try to understand what does it mean with respect to the data that we have. And also cheating can manifest in consecutive failed login, right? So let's say that I have this bot and I want to log in from another client on another even source IP or Cedar IP, I'm sorry, subnets, and that can be posed as an anomaly or non-legit behavior. In the case of microtransaction, it is very similar to any fraud that you might have in other venue, even like a credit card cheating fraud. And the player move anomalies, players walk and shoot in the opposite direction while performing other tasks. You have mentioned that as well. So how can we stop cheating in the game? So usually if you are a game publisher, you would, and this is going to be a business problem, a business risk for you, you're going to form an anti-cheat team. And the anti-cheat team will comprise of at least 3 types of personas, right? The first one who are the people that are actually the marketing team, that are very involved, or designers that are very involved with the storyline of the game. On the other hand, you will have people that knows how to pull the data from all the sources that you had, including the relational database. And finally, you will have the data scientist that's going to make a decision what, given the data that you have, what will be the best model or algorithm you should use in order to get those cheater with good efficacy. The reason that it's important to have a multidisciplinary team is because that anti-cheating, a false positive, can be frustrating in the same way, right? You don't want to have a situation where legit users will go and have to go through all kinds of horrible captchas, verification, and also like just going back and forth with customer care. That's going to create the opposite effect of the whole motivation, right? So I guess that what we wanted to enable by forming this anti-cheat team is to stop those cheater and continuously refine the algorithm. So now we're going to go over to review the data structure, and again, we try to keep it as light as easy as possible without getting too much into the weeds, but hopefully the level of details with the schema that we're going to show you now, will give you a sense of how you do stuff. And by the way, before I continue, all these things going to be, all this presentation and the code is going to be open source and be available for you to try after that. So you don't have to take notes and read those small prints. So in the first data set, we have the player authentication. This is the authentication transaction. As I said, there is a timestamp that the player came, and in this case, it started to, the authentication method was the Xbox Live token. It means that it logged through the Xbox authentication service, even if you are, you offer other players to log in from another places to the same game. This is the player GUID, the user agent, which in this case it's an Xbox device. This was the source IP and the seeder and the geolocation, the geographic location of the players. The transaction is again the timestamp, the player GUID, and the type. In our case, it's a loot box. The user agent again, and as you could sense from the transaction and the authentication, you can also see how these two data sources can relate can be joined on the player GUID and the user agent as well. And finally, we have the player moves. The player moves in this case is the X and Z coordination, include the timestamp and the player GUID, of course. But we also have three properties. One is the quadrant, as you saw in the video clip that I shared. The game is divided into quadrant and in sectors and subsectors in each quadrant, and the events can be a user traversing from one place to another, or forging or dodging, or other events that the game allowed. So we used three models for this game data. The first one is the authentication. Now, for authentication, we use the algorithm called IP Insight, and again, it's an unsupervised learning algorithm for detecting anomalies for specifically patterns of IP. This algorithm does a really good job by looking at patterns in the source IP and the seeder of the subnets of the IP that the player come from. For transaction, we looked at supervised linear regression, specifically a logistic regression that basically takes the classified data and produce a number between 0 and 1 with respect to the transaction that was made. And again, this is a very similar problem to fraud detection with credit cards. The reason that we use supervised, it's because the data that we have for authentication is already resides on Aurora database in our case, because it serves the customer care. And if someone if someone complains about some transaction that was made on his account, or something that was done by other players, this information is already resides in Aurora. So supervised classified algorithm is optimal here. And finally, for the player moves, we use the random cut forest, just because that we have lots of information, and this information is not classified. We don't even know if it's how to even start with classifying those events. And so the player moves fits very well to the business problem that we have, because we assume that most players are good and they are playing nicely according to the rules, and so the anomalous behavior will be suspicious, will be considered as suspicious for us. So the data preparation. So just to give you an idea of the amount of data that that was included in this experiment, this simulation, we have 700,000 authentication event, and 1,400,000 transaction, and roughly 65 million player moves, right? And this is between 0.1 and what we did, for the anomalous, sorry, for the supervised data, we classified data between 0.1 to 3% to allow the model to distinguish between legit transaction, move, authentication, and other, and non-legit, I'm sorry. So we build our models, as I said, using Jupyter notebooks hosted on by SageMaker. We used all the data to store. We stored all the data on S3, and then once that we have the training, once that we were able to distill the data and train the model, we deploy the model with a hosted inference endpoint using the SageMaker service. And we, as Yoav showed before, we used Aurora to invoke the endpoints. And we're going to talk about how we did it and all the optimization that include with that. Now, and now we get into the meat of how this this journey on training the data and massaging the data using using the high level language SQL that we use, make it easy, and I guess more cost effective in some way with respect to the personas and of the people that are participating in the anti-cheat team. So the example, and again, I'm not a data scientist. I feel very comfortable with writing SQLs, and so the ML models like numbers, and I mean integers. And in the data that I got from all the sources that we mentioned, there was, as you saw, some of them were presented as characters. Some of them was presented as numbers, but those numbers also needed some processing. So what we wanted to do, we wanted to encode the string attributes into a number that the models can understand better. So for that, you want to run all kinds of transformation and encoding processes. For example, we transform the move event. So in the example that we showed before, we have an event called traverse sector or travel explore. We needed to encode this to an integer. In the sector case, we have a sector 0 dash -2. In this case, we wanted to encode it into a string, and the same thing for the quadrant that the player play. Now, if you do it, and this is how I did it, I'm going to share I'm going to open source the notebook so you can actually see this code sample. But in this example, this code sample is taken from the notebook that I authored. But as you could see here, I took the quadrant encoded, the sector encoded, and the event, and encoded it using the pandas and the what hot encoder. Now, it's not a rocket science, and and if you have a good understanding of Python, you could get along with that. But if you're not a data scientist and you're not comfortable by jumping between all kinds of platform, if we take this thing and use this example, this example does the same thing. It's basically, if you look at that, it starts with select distinct all the event name, and this is just for the event encoding, and basically go through all the encounters table and just assign an integer to each event. So this is fairly simple, as it is, I think, the simplest SQL that you can come up, and you didn't have to do all this exotic libraries that I respect very much. But for the personas, again, bringing back the business problem that we have, the personas that we are that are dealing with this anti-cheat team are not necessarily comfortable with that. So that's another value proposition. Okay, so let's try and see these things in action. So the way that we do it, we created materialized view for the 3-dimension, the authentication, transaction, and the encounters, the player moves. And based on the characteristics of the cheating that we discussed, we're going to start by looking at suspicious transaction, then looking at suspicious authentication by the player who executed the transaction, some sort of like a join, and then we're going to try to make sense of this suspicious activity by looking at the 3rd dimension, which is the player moves. Now, the order that we decided on is completely arbitrary. It's because of how Yoav and I looked at the business problem, but it does not preclude you from applying any flexibility to your anti-cheating strategy. Materialized view. So we agree that we are going to, on a hourly basis, weekly basis, daily basis, whatever the frequency that we want to apply in the online processing of this anti-cheating, we created this this materialized view, and this materialized view is triggered by a trigger, the same sample that you have showed before. But if you look at this example, you could see that we are querying all the in the authentication case, we're querying the entire authentication. Sorry, we're querying the parameters that are the input for the authentication model. In this case, it's the day, month, hour, minute, and the source IP. And we basically filtering only the suspicious one, the one that are mentioned as a CLS that is greater than 0, classified as fraudulent. For the move, it's fairly the same thing, but as you could see here, we query the model for the move cheat square, the player Z, quadrant, sector, and event. But in this case, we chose to get only the transaction that was classified above 2. Why 2? Is because that we used the data and we looked at and we created like a simple histogram, and we saw that an anomaly with that its score is greater than 2 is suspicious. So as you could see, it's very flexible and very fluid, and really depends on your game and your data. And this is and the tools basically exemplify the flexibility of this model. Okay, so let's run this thing. So I'm going to share my other screen. Okay, Let's see. Okay, so I'm going to log in, and so the first query that I'm going to execute is going to basically, hey, can you give me all the timestamp and the player GUIDs that are basically are suspicious. So I'm going to go through all the, I'm going to call into the transaction cheat score, right? And I'm going to query the materialized view that created just an hour ago, okay? Between the time that I specified. And so as you could see, we could I mean if you could see here that the syntax that I'm using here, I'm basically querying the materialized view and going back into and looking and filter only the suspicious one. In the last slides, we're going to see how the optimization, how the Aurora ML feature is optimizing the back and forth between the machine, between the database and the endpoint, because obviously there is a lot of optimization opportunity with respect to the network and the network latency between the two. Now, if we looked at the 13 rows that we got here, we have, it doesn't mean so much for us at this point, but what we could do is we can, oops, we can, come on, sorry. We're going to look at another query that's going to basically look at the authentication, transaction, and going to join it with the suspicious transaction that we have, okay? And as you could see here, 1 second, I'm going to do the same thing, and we're going to talk about those things. As you can see here, these are the authentication sheet, right, joined with the transaction sheet, right? So what we basically did, we were able to filter these 13 cases, okay, suspicious cases, to 3-1. And if what we could see here is that we have a really interesting player here that is doing something. So let's try to understand what's going on here. The first timestamp is describing the timestamp of the authentication. As you can see here, this guy logged in in 6:37 in the morning, and the suspicious transaction, which is denoted in the second timestamp, the suspicious transaction happened roughly 20 minutes after he logged in. Let's look at another transaction. The same thing, 6:37. That's probably the same authentication that was made, but here we see that another transaction, another suspicious transaction happened in 11 p.m. The same thing happened at 4 p.m. and sorry, he has another authentication transaction at 4 p.m. and then another authentication, suspicious authentication happened in the same time, right? So that looks a little bit suspicious. So what we want to do here, we want to basically go and try to see, to cross-reference it with other dimension. And the other dimension that we have here is the player moves. So in the player moves, we are going to execute this transaction, And this transaction, if you could see here, it's returning all the distinct timestamp and player GUIDs of the the the, um, the suspicious moves. And how this suspicious move manifests, you could see here, I'm basically querying the the move cheat score, right? And I'm asking to filter the move cheat score from the materialized view that are greater, that the classification is greater than 2. And again, I'm classifying it, I'm limiting it between the timestamp that I was able to get here. Okay, so what did we get? We got here, we got that this player, right? We can see him here. He did some suspicious move, and this suspicious move happened in 7 a.m., which is like something like 6 minutes after the transaction, the suspicious transaction that was made that day. So you could see that you could get an idea that this is something that is an interesting player to explore. And we as an anti-cheat team going to take these details and go and explore more. We might want to look at the log of all his all his movements and try to assess whether there are other suspicious behavior, or maybe look at patterns. So what we wanted to show you here is that the game that we presented includes lots of movements, lots of transactions that are coming at you from all kinds of direction. And what we were able to do, we were able to show you with 3 select statement, we were able to get a good idea of what's going on with respect to the cheating in the game. So let's go back to the slide and see. I'm going to new share. I'm going to PowerPoint. I'm going to share this thing back. Okay, so this is what we did. We query first the authentication. We found these 13 cases, and then we joined these cases with a transaction, and we found this case, and then later on we were able to look at some anomalies that in his moves, right? And as you could see also that there are cases that are anomalous that are legit, right? And we didn't necessarily wanted to take action upon them, and that's allude to the point that I was making before about false positive. Now, and this is something that I didn't do, so I can jump back to the command line, but basically the things that I wanted that we wanted to do as a next step is to look at what's going on with their moves, why the moves were suspicious. And here we double click basically into the transaction that this guy did, regardless to the models, right? We basically queried the movements that the player did, and we found, and this is how it looks like, just to give you an idea. It's I'm basically looking at the timestamp, the player GUID, the quadrant, and the sector of all the cases that was suspicious, right? Where classified is greater than 2, and we found that the suspicious behavior happened in quadrant 3, sector 35. So what we will do is that we will go to our encoding mechanism. We're going to find out what's going on in this thing, and we're going to start monitoring other activities in these areas. So now, it's all good. It's great. We were able to find those cheater, hopefully, with not so many false positive. But let's but in I also want to spend some time to understand, to show you how we optimize the calls, because if you think about it, the calls between SageMaker and Aurora can be very chatty, right? And this chattiness can create several problems. First of all, the first problem can be latency, right? You don't want to sit in front of the if it's in front of the screen and wait for long hours and long seconds or minutes. But also this back and forth, this chattiness can manifest in cost of data transfer, right? Think about the cost that because you have two separate endpoints that are talking to each other, and that can also can incur cost. And finally, if you think about the ease of use that you gain by the seamless integration between these two endpoints. For example, you might want to apply a asynchronous mechanism when you are interacting with the API at scales by partitioning the data and sending those chunks in a batch fashion. And we're going to show you how this done in our specific example. But in this case, what we wanted to show here is that we're going to look at how many fetches was made between the Aurora database that was originating the call to the model and to the SageMaker. So we're going to start by flashing the status of flashing the buffers of the statuses. And now, if you look at the command that we executed here, we are going to get lots of data, which is basically roughly 1750 rows, right? And if we looked at the number that we made to the Aurora, to the SageMaker, you could see here that when the transaction table that we query was 1.3 million records, and the 1.2 million of them hit the cache, right? So what we were able to do, we were basically optimize the number of back and forth between between Aurora and SageMaker, and basically only 1,351 actual request was made. And this is actually a really cool optimization that if you would have to do it yourself, you will have to apply those mechanism and caching yourself, which is will not contribute to your business as an anti-cheat team. Now, I also want to point out for another another optimization when we were that we demonstrated here. We were making a request, right? In this case, it's the Aurora integrating with Amazon Comprehend, but it follows the same pattern when it interact with the SageMaker. The application, you make a call to the application returns 50 features, for example, right? And now you need to communicate that to the other API, again, the Comprehend case. And Comprehend as an API has a limitation of 25 rows in each batch, right? So what you will have to do in this case, you will have to break to batch those requests, those 50 requests into two chunks, right? So you're gonna get a response, send another request, and get another response, and aggregate that. Okay, so that's something that you will end up doing if you would do it to yourself. What we get from here is you want to have both scalability of requests from the comprehend. You don't want to implement asynchronous asynchronous query, as I just demonstrated. You as a user want to basically make a request and get the results and wait hopefully until these things finish, but you don't want to deal with this asynchronous. But the asynchronous fashion is required to get a scalable query mechanism. All right, so that's what we had for today. We have we published our example on GitHub that basically talks about those all the things that we demonstrated today. We have other interesting links for you about Amazon Aurora and the machine learning, other features that you could use, or in best practices, and the Amazon SageMaker. I really hope that you that was a good use of your time. I enjoyed it very much. This is Yoav and my contacts. We are happy to answer questions. Yeah, thank you very much.
Yeah, thank you very much, Yav. This was great. And yeah, looking forward to hearing from people in the Percona community. And if you're doing gaming or if you're doing other types of applications, I hope you can use similar techniques. So would love to hear from you. Thanks very much.